Okay, Bismillah ar-Rahman ar-Rahim, wa salatu wa salam ala ashrafil mursalin Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. So today, inshallah, guys, we're going to be looking at the performance of a Kalman filter. After you implement the Kalman filter, you've seen, okay, in the end, there are just a few equations that we implement in the code. If you already take the sensor readings, whether they're proprioceptive and exteroceptive, and connect it to a simple way to the Kalman filter algorithms, you need to define the state transition model and the measurement model. So that's your job to actually identify all of this stuff. And afterwards, you just tune some parameters. So today, we're going to be seeing some parameters, how they affect the performance of the Kalman filter. And afterwards, afterwards, we're going to be extending the 1D robot we had and you had in the assignment to a 2D problems. You're going to see how it changes. Even though the equations are the same, it's just everything becomes a little bit bigger. And then we're going to be looking at a motivation. So the topic afterwards will be very important. It's called the extended Kalman filter. And today we're only going to be giving some basics of that. Okay? And next lecture, inshallah, we're going to be looking more into details about how it looks like. And this will be what we're going to be doing in the next assignment. Okay? So let's start with the recap. So we said that what we're doing in this topic is that we're representing the state of the robot, which can include its position, its velocity, and in general, its orientation. So the whole pose and the whole velocity, angular and linear, and more. You can even do more stuff here in terms of the state, and this will be clear when we talk about the IMU next in the coming week, inshallah. So the state of the robot X, you want to estimate it using this Gaussian. So we assume we have a probability distribution function of the state X given all of the data that we know about the system. So Y here is all of the data that we have through the system. So this includes all of the sensors that we have and even the previous states that we had earlier about the robot. And then we said that the Kalman filter is a type of a Bayesian, it is one implementation of the Bayesian filtering problem, where you start by a prior belief and then you update it into the posterior belief into two steps. You first do a prediction update using a state transition model, and with that you use the U. The U here was the input. We called it a control input, and it corresponds to the proprioceptive sensors. And then after you get this updated belief, so we update it again. Okay, so this predicted belief, we update it again using the correction with the exteroceptive sensors. So this is how usually it works. So you do one step update with the prediction, and you do another update with the correction. Okay. And the first step, we use the proprioceptive sensors, and the second step, we use the exteroceptive sensor. This is Muhammad.
Does the two sensors have to measure directly to the two states, the two whatever they want to sense?
So that's an excellent question. So are you saying that should they be exactly the same state, or should they be related to the state?
Not related to the same state. For example, we have accelerometer.
Okay.
It's calculate the acceleration.
That's right. Accelerometer calculates the acceleration.
And we have another, like from the camera.
A camera?
And it's sensing whatever the surrounding is.
Okay.
The shape of
It will measure, you can get from the raw image, you can do some post-processing, and then you can transform it into some velocity of the robot. You can do that.
Okay, so I have to, whatever sensor I have to make it the same output in the end, whatever I get.
But that's not the same output, right? So the IMU will give you accelerations,
Yeah,
and the camera will give you velocities.
Yes.
Okay. So are they the same measurement? Are they the same state?
They don't use the same measurement, but they can derive the same.
They are related to it.
Yeah.
Exactly. So the proprioceptive sensor is related to the state through the state transition model. You see the U here affects the X, and the exteroceptive sensor affects the X through the sensor model. So remember, I mentioned this a lot, several times, that we say that this is the sensor model and this is the state transition model. Even both have sensors in them. There's just, the standard literature for the Kalman filter. They always call the U the control input, and they said the Z is the measurement or the observation. Even though here the U is a measurement from a sensor and Z is another measurement from a sensor. Okay, and they are definitely related to the X. Okay? Whether, for example, that's a very good question. Because if you think about it, can I use, for example, a temperature sensor to try to estimate the position of the robot?
Yes. Depends on the situation.
What situation?
Like, let's assume there is a competition.
Okay.
It's a heated pipes.
That's another problem. Okay, that's very good point. Yes. In case the surrounding itself has some heat signature, has some thermal signature, you can use that to actually identify where the robot is. That's possible. But that's not the thing. So if I just give you a temperature sensor, okay? For example, I put a temperature sensor on my arm and I start moving my arm. Can I know where my arm is from the sensor? Okay? There is no relation, right? The temperature does not affect the movement of the arm. The same also here. So you see here, the sensor model and the state transition model, they capture how both are related together. And there is some advanced analysis. This is way beyond your course and even your whole specialization as aerospace engineers. So this is actually something we do in control theory. We check something called the observability of the state. Whether can I observe the state from the measurements or not, that's another story. Okay? So this is usually inside, this is usually a problem. We're assuming here in the Kalman filter that the state is observable from the sensor that I have. Okay, but that's related, I think, to your question. Clear? Okay. So the sensor model and the state transition model, they capture how the state is related to the sensors we have. And then we said that the state transition model, okay, it's probabilistic. It's not just an equation. You see, we have here, we said xk minus 1 is a Gaussian, and vk is another Gaussian. And we said that, we saw last time that if I know the Gaussians of the xk minus 1 and the vk, and when I say I know the Gaussian, it means I only knew two things of the Gaussian. What are they? What are the only two things you need to know about the Gaussian? The mean and the covariance matrix. Not the standard deviation, the covariance in general. And then we saw that the measurement model is also, again, with Gaussian. So we have the Z as an input, the xk as a Gaussian, and the wk as a Gaussian. We said that we related the Gaussians here to the beta k. And the equations, we saw them, okay, you saw them again and again in the previous slides. We had two problems. One, which is a simple toy problem, it's a 1D robot, and another one is a simple, again, 2D problem of a robot position and velocity estimation. In this case, we have only the state of the robot to be the position. We have one velocity sensor and another position sensor. And then in the 2D problem, we said that we have position and velocity, and then we have the acceleration measured proprioceptively, and we have the position measured exteroceptively using these two sensors. Okay. And something that you can actually identify from this problem, and I'll come back to it later because we're going to look at this example today. You see, I only have a sensor for the acceleration and for the position, right? And yet, I can get out of the Kalman filter an estimate for what? What is something that I'm not measuring here, but I do have an estimate of? Yeah. The velocity. You see? Even though I have just the acceleration sensor and a position sensor, I'm actually getting something better out of the Kalman filter. I'm getting both the position and the velocity. And one might think, you can even ask the same question here. In the example that you had in the assignment, so in the assignment, the problem that you had in the assignment, you were given, I told you to estimate the state of the robot, even though you had a sensor for the position. Okay, so here we wanted to estimate the position of the robot, even though you had a sensor for the position. So why the Kalman filter in the first place? Did anyone think about it when you were doing the assignment? Why did we need to actually have an estimator? Why did we do all of these equations so that in the end we can get the position of the robot while I had already a position sensor? Sorry? One of the points is the noise, that's for sure. That's correct. What else? Let me re-ask the question. If I give you a GPS, okay, and I tell you use the GPS to know where the position is of your robot, and you take the robot and you go out in the desert, is it enough? Just read the GPS measurement and then you know exactly where the robot is? No. You need to add more stuff. For example, your phones, the example of the robot here is your phones, they have the GPS on them. But not only that, Google Maps does not use only the GPS to identify where you are. It uses even cell phones. You remember, you all have seen, for example, that sometimes Google Maps tells you to open the cell phone, the mobile data, so that it can give you a better accuracy. Why is that? Because it's using the cell phone information to give you better estimates. It also uses the IMU on board that you have. And all of this is done in a big Kalman filter so that, or a state estimator in general, so that you can get better positions. So even though I have here a position sensor, why would I be interested in estimating the state? One of them is to reduce the effect of the noise. What else?
Do you want to make the position more certain?
More certain, but that's related to the position. That's related to the noise part. Sorry? That's related to the certainty. That's correct.
Also, let's assume it's not a robot, it's like a rocket.
Okay.
You could make more sure that it's going to hit its target.
That's the same. Even if you have a robot, well, independent of the application, you always know where the object is, where the robot is, whether the robot, the phone, or the rocket, whatever.
What about the future?
Sorry?
The future. So it's going to be constant at that speed.
But it's the same. Same idea. Whether we're interested in the robot being in that place exactly to do a task, or the rocket to hit something. Sorry? Almost there. It's yes and no. So the answer is, you remember what we had in the position. I'll actually come back to that point. So I'll keep that question. I'll come back to it when we start talking about the lecture. Okay. And here you see, in this problem, it's actually clearer. I had a position sensor and an acceleration sensor, and I was able to get out of the Kalman filter more stuff than I'm just sensing. I got the velocity out of it as well. Okay. So these were the whole idea of how do we do the prediction update. So the prediction update step is simply you take the mean and the Gaussian of this. Sorry, you take the mean and the covariance of this Gaussian, and then you calculate the mean of the covariance of that Gaussian. And in the correction update, you take the mean and covariance of what you just calculated, okay? And then you update them so that you can get the mean and the covariance of this. So this is the whole idea. So abstractly, this is simply what the prediction and correction update are. In the MATLAB assignment that you had, they were just implemented for you, and you just filled in the equations in the two files, the Kalman update and the Kalman predict files. And these were the equations that you had. I think this was the missing part in the assignment, right? These were what you needed to fill in, right? Or not? These were the equations that you need to fill in, okay? Only these two?
Yeah. Prediction was one thing.
Okay. And the other one was the update, the correction.
Yeah,
You were supposed to do both or only one?
no,
Both, right? So in one file you had to write these, in the other file you had to write this. So they're only in the end 2 lines here and 5 lines here that you can just implement. Okay, that's it. That's the whole algorithm. And of course it runs recursively, so you keep on running it again and again and again. Okay, and this was exactly what. So this was the block diagram. Okay, so these two. So you take the mean and the covariance. After that, I do a prediction with the control input u, and then I do a prediction for the covariance. So you see here, this is the prediction step. And after that, I compute the innovation and the covariance of the innovation. And afterwards, I calculate the Kalman gain. And then I use the Kalman gain to correct the state. And I use the Kalman gain again to correct the covariance of the state. And in the end, I have the state and the covariance after, the whole time step k. So this is a time step k, and this is a time step k minus 1. So all of this is just what runs at one loop. Okay. And one thing I want to highlight here before we move on is that everything that you see on the top here is actually not related to the robot. It's not actually related to the algorithm. The algorithm is only what's beyond this dashed line here, while everything on the top is the real robot itself. Okay. And you see here, I'm measuring here, for example, what the U is, which is the proprioceptive sensor, and I'm taking from here, from the real robot, the Z, the exteroceptive sensor. That's the only thing that I'm using for the algorithm. Everything else is just running internally. Okay. And also one more thing is that you see in all of the algorithm here, at home it will be clearer. You see the F, the Q, the B, and the H, and also the R matrix here, they're all in blue. Okay? And all of these matrices, they come from the real system. So this is based on your model. Okay? So after you do mathematical modeling, after you identify how the sensors affect the state, you use that information inside of the algorithm itself. Okay? And this was the assignment that you did. And then you start playing around here by the position. You just move the robot back and forth, and you've seen the Gaussian, how it changes. So this was the estimate about where the robot is. And here you were seeing the history of the robot as you did the assignment. Now let's take a look at, let's analyze the results that you got in the assignment. So you were asked to do 2 experiments. Okay, the first one, you started by, so in the first experiment you had an initial mean error. Okay, so, and in that case, the true robot, for example, started at position 5, and you were asked to make that the initial guess was very far from it. Okay, and afterwards you started to move around. Okay, and you see after one time step, okay, the position error is very big. But after we got the measurement, the green circle here, it quickly, okay, was corrected, quickly converged to the real one. And afterwards, you just, okay, kept on moving this way. Okay. In this case, the measurement frequency was 1/8. So the frequency of the position sensor was just 8 seconds. So the time step, the time sampling was 8 seconds. The variance of the measurement was 0.01, and the control variance was 0.03. Okay, so you played around with these numbers, and this is exactly what you were supposed to do. You were playing around the 0.01 and 0.03 here. And in this second case, when we changed the variance of the measurement, the real variance of the measurement, the measurements became very noisy. Okay, you see here the measurements became very noisy in that sense, and we also increased the frequency. Okay. Actually, we increased the frequency here. It was 1/8, and here it was 1/2 in that scenario. And you see, I'm getting here the measurements every 2 seconds, while here I'm getting the measurements every 8 seconds. Okay. Here the measurements, they come at every 8 seconds, but they are very certain. You see, I have very low variance, which is 0.01. But here I get them every 2 seconds, but they are very noisy. Okay. They have a variance of 0.9. which is 0.9 divided by 0.01 is 90 times more. Okay, the variance is 90 times higher between this scenario and that scenario. Okay, so you see here the whole idea of the Kalman filter is that it can actually, first of all, you can recover from the poor initial guess. So it's not important that you know exactly where the robot is initially. It will correct itself. That's one thing. The second thing is that even if the initial estimate is far off, it will correct for it, the measurement. And the Kalman gain is actually the thing that the key the key secret here is the Kalman gain, the K that we calculate. And this is the one that actually merges the correction and the prediction together. And how do you choose the RK and the QK? You see here, in the first case, the first experiment you're supposed to do, the RK was less than the QK, which means that you're saying, so RK is how much you trust the measurement, how much you trust that the Z is correct. And the QK is how much you trust that the motion model is correct. So you have a prediction, okay, and that's the Q affects it, and you have a correction, the R affects it. So by playing around with the R and the Q, you're telling the filter trust more the prediction versus the correction. Exactly. So the prediction is using the state transition model, while the correction is using the measurement model. So you're telling it, trust one or the other. In this scenario, it's trusting more which?
The model.
State transition model or the measurement model? So in experiment A, is it trusting more the state transition model or the measurement model?
Okay.
Think about it first. Who says the state transition model? One?
What is the input for the input is the control, right?
The input is the U,
Which is the control.
which is the proprioceptive sensor, the control input, yes. And the Q affects this prediction. And the R affects the correction.
The correction is the other one.
The correction is the one on the bottom, which exactly is the one which is the exteroceptive sensor. So here is it trusting more the prediction or the correction?
No, I think the first,
This one?
yeah, I think it's the prediction more.
Who says the prediction? 1. Who says the correction? Correct. You're correct. The correction, actually.
Why?
Here, you're saying R is smaller.
Yes.
And R is the variance of the correction step, is of the measurement. You're telling it, my measurement is actually very good. So whenever you get this measurement, what should you do? Trust it. So you see here, when we got the measurement, so actually in this step, so you see here, why did it jump very high, from this step to that step?
He trusted the measurement.
He trusted the measurement.
But look at the prediction, the projection of the line.
Yeah,
It's going 8 seconds unknowingly. He doesn't know what's happening.
that's correct.
But he's going for it until he gets the second measurement after 8 seconds.
That's correct. You see here? And that's why in this case, you started to have an error. For example, take a look. I cannot zoom here. So you see what's happening here? This is very clear, right? Between this measurement and this measurement, you have a big error, and it's not being corrected. But after you get the measurement, you jump very high. You forget about actually that you have this prediction, and you're trusting more the measurement. So that's what you see here. In this scenario, we are not trusting the measurement very much. Why not? Why can you say here that we're not trusting the measurement?
He's not following the whole.
So what should you expect here for the red line? If it was trusting the measurement more than the control, more than the state transition model.
He will be.
Yeah. Say.
It will be more accurate and more similar to the measurement than.
More similar to the measurement than the prediction, exactly. So actually it will be more fluctuating. You will see that the red curve should have had more noise. You had this, I think, in the assignment, right?
Yes.
You played around with it. When you increase the trust in the, so here, when we increase the trust in the model, so when we increase the trust in the measurement, and the measurement is noisy, like in this case, you'll find that actually we have a very noisy signal. But here, because RK is we told the filter RK is much bigger than the QK, so we're telling it don't trust the measurement and trust more the prediction. You see actually it's being more smoother, and it's not being affected by the noise of the measurement here. Okay. And now back to the question that I asked you earlier about, in this scenario we have a position sensor and yet I'm using a Kalman filter. What is the main benefit of it? If you did not have a Kalman filter and you're only trusting the measurement, then you don't know about what's happening to the robot until you get the next measurement. So for the whole 8 seconds, for the whole 7 seconds between this measurement and that measurement, I'm completely blind. Or in other words, the robot is completely blind about where it is. It doesn't have this information. So I only get one piece of information here and then one piece of information there and so on and so forth. If you, just to make it clear, if you're only using GPS measurements and you're driving with Google Maps, you'll find that at one point you're on the road and then you disappear. And afterwards you get one reading on the road and you disappear. And one reading on the road and you disappear and so on and so forth. You just keep on jumping like that. But of course now when you're driving you find that you're following the path right and you're going right and left. This is because the Kalman filter fills in the gap between both. It gives you a prediction at much higher rate than what the measurement gives you. So here in this scenario, we had a measurement every 8 seconds, while the state was updated every 1 second. Whenever you press the right and left buttons, every time step, you're always seeing how the robot moves. You have an estimate of where the robot is. Okay? So is that clear? Okay? So with the Kalman filter, I can boost the update rate of the state, okay? Even beyond what the measurement can give me, okay? That's the whole idea of the prediction model. I can use it to predict even when I don't have the measurements, and when I have the measurements, I just correct. Okay. Okay. So is that clear? So this was the analysis of what you did and you experienced in 1D. Everything we talked about in 1D can be extended in 2D, okay? So this was the model that we had in 2D, the one that we have. I want to estimate the position and the velocity. I'm measuring the acceleration and at 1 hertz, and I'm measuring the position at 1 over TS. Again, some number you can play around with. And the kinematic model is that rate of change of position is equal to velocity, and rate of change of velocity is equal to acceleration. The state transition model, we derived it on the board, and it was shown to be like that. Okay? So again, this is one of the things you might experience in the quiz, to transform a kinematic model into its discrete model by just using this equation again and recursively, so that you can get something like this. Okay. So the question would be, write the differential equation given into a state transition, into a discrete state transition model. Identify what is the f and the b and and the h and so on and so forth. If we implement the Kalman filter, so you're not going to be implementing this. You're going to be given the codes. You can play around with it at home if you want. So here, when we start, okay, for example, this will be our starting point. Let's say, for example, we told the robot we don't know where you are, so we give it a very big ellipse, this circle, and then afterwards we get a measurement, and you see we just keep on following the measurements, and we trust the measurements more, and so on and so forth. So this is usually what you have in Google Maps, right? So these are all of the circles that that you follow, and the center of the circle is simply where the mean is. How where the Kalman filter is telling you about where it thinks you are, the mean of the Gaussian, and the circle here, okay, is simply like how big or small you can trust the estimate, because it's related to the covariance. Okay. And again, this is larger ellipse and smaller ellipse, so that's some stuff you can read at home. What I want to tell you a little bit about here in terms of mathematics, what is the circle you're seeing? Okay, what is actually this circle? How can you compute it? And this is related to something called the confidence interval of a Gaussian. Okay, and to explain it, let me explain it first on the 1D, and then I extend it to the 2D case. You remember this is the shape of the Gaussian, right? So this is you should be familiar with that. And its center is at the mean, okay? And afterwards, you see the blue region here, okay? It is between u minus sigma and u plus sigma. What is the sigma here? Sigma? Standard deviation. Sigma squared is the variance, sigma alone is the standard deviation. So you see here, the blue region is simply the mean plus or minus the sigma. So when I tell you, for example, when you say my sensor, okay, gives me a reading of 5 units, any units, okay, plus or minus 1, what do you mean by that?
4 to 7.
What is 4 to 7?
The interval.
4 to 6, you mean? 4 to 6.
4 to 6.
Okay? So my sensor, when you say the sensor is giving me a reading of 5 plus or minus 1, okay, you transform this into from 4 to 7, right? What is from 4 to 7? 4 to 6. 4 to 6. You infected me.
Let's take you took a reading.
Okay.
For the same thing, and it shows that it's 3.
Okay.
Then this is you can't trust it because it's outside the confidence interval. Or you say it's.
Okay. Let me rephrase the question. Okay. This is actually a big, misconception, and I'll show you now that you'll be divided into opinion. So as engineers, okay, you go and you open the data sheet and you find that this sensor has a reading of something plus or minus 1. Let's say that this something is 5. So I'll ask you 2 questions. First one, does this mean that always the reading of the sensor will be from 4 to 6? All the readings of the sensor will be from 4 to 6 if the true value is actually 5. That's the first thing. Or it's telling you that the readings can be most likely from 4 to 6, but it can be also less than 4 and bigger than 6. Who says the first option? Who says that the reading will always be from 4 to 6? 1. Who says that the reading can be from 4 to 6, but can go even beyond 4 and beyond 6? Okay, the majority. The correct answer is that. The second one, the reading can be less than 4 and bigger than 6. No, it's not about the error. No, it has nothing to do with the error. It's just about the probabilistic nature. When you say plus or minus some number, you're actually talking about the standard deviation. You're talking about this blue region here. So the data sheet of the sensor is telling you that 68% of the measurement, 68.3 to be exact, 68% of the measurements, I can guarantee to you that they will be at the mean plus or minus the number I'm telling you about. So the real value, okay, plus or minus something. Yes, Mohammed.
Let's say I'm a quality control.
Okay.
And I have multiple sensors. I
Yes.
have one sample, and the manufacturer tell me that it's. I'm confident that it's gonna be from +1 -1, whatever, 4 to 6.
Exactly. From plus or minus 1. Yes.
I'll take multiple samples.
That's right.
And then I found out that most of it, I'll actually take a measurement outside of whatever.
What is most of it? That's exactly what I'm talking about.
They say, for example, it's a normal distribution.
Okay.
I would say like 68%.
68%.
So I took the sample.
Okay.
If it's more than 68%, if it is more than the whole shipment will be rejected.
That's correct. That's exactly what I'm talking about. Yes. So, but what you should check, okay, and that's the misconception, you should not check that all of the measurements are from for example, between -1 and 1. Let's say, for example, that the mean is 0. Okay. So don't check that the measurements are from 0 to 1. So from -1 to 1. Then you're thinking about that. Then the variance you're reading is actually correct. If you want to know the value around which 99.7% of the whole measurements will be, they're actually the 3 sigma, not the 1 sigma. You see the point here? Yeah. So if I tell you plus or minus 1, and you want to know what almost all of the readings will have, they will actually be from -3 to +3. So -3 sigma to +3 sigma. Yes, sir. Excellent point. That's a very good question, Omar. So, do I always assume that the real, thing is actually Gaussian? Of course not. But why do people use the Gaussian? It's just because, it's better than nothing. In real life, you don't know what the probability is. In real life, you don't know exactly. You have to take. How can I get this probability from the real thing? I have to take almost infinite samples of the whole thing, and I keep on, just doing it again and again and again. So one thing that you can do actually is, if you're working, in quality control, you can look at the history of all of the things that you're getting from this company, I'm getting the readings, for many years, and I'm checking that I'm keeping track of them, and they're always, distributed in this way. Then you would say that actually this is the real distribution of it, and I'm not going to assume it's a Gaussian. Okay, so that's usually how you can do it. Okay. So is that clear? What does the confidence interval mean? Now the confidence interval, this as a concept in 1D actually extends simply to 2D and 3D very easily. And when you extend it to 2D, you have the equation of the ellipse. You remember the ellipse that we saw when we looked at the multivariate Gaussian, the 2D version? So this line here, I can also, similar to what I drew here one like plus or minus some number, okay, the sigma, and 68% were in this part. I can also have the 2 sigma and the 3 sigma. These 3 lines also correspond to the 1 sigma, the 2 sigma, and the 3 sigma. Okay? So the 3 sigma ellipse is where 99.7% of all of the dots, okay, which are all of the x and y values here, will live. And the pink one, this dashed one here, where all of the 95%, and the 3 sigma, the 1 sigma is where about 68% of the values will live. Okay. So what is the ellipse that was given by Google Maps? Honestly, I don't know. I don't know whether it's the 1 sigma or the 3 sigma. Okay. Or the 2 sigma, I don't know. But that's something for you to look at. Okay. So try to Google it or to check out for yourself. So when ChatGPT tells you, when Google Maps tells you, this circle, and I trust you're in this circle, is it telling you that 99.7% you'll be in this circle? Or is it telling you 68% of the time you'll be in that circle? Or it's certain that you'll be in this circle? I don't know. Something for you to check out, okay, if you're curious. Is that clear? Okay. How this confidence intervals extend from 1D to 2D? Clear? Everyone? Yes. How much?
So they say it's in the 68%.
68. So it's a 1 sigma. Okay. So what Google Maps tells you, So you're actually in the 1 sigma region. You're in the 1 sigma ellipse. And it doesn't show you an ellipse, it shows you just a circle. Why?
Simplify for the user.
Does anyone remember when does the ellipse became a circle? When we were playing around with the multivariate Gaussian, the animation? Exactly what you were saying? Exactly. We had no covariance. The covariance between the x and the y was 0. And the variance, okay, was actually the same number. So the variance of the x and the variance of the y was assumed to be the same number. And that's exactly the assignment that you had. Remember, you were asked to simplify the multivariate Gaussian, the 2D version, and you had sigma x squared and sigma y squared and zeros. This is actually the same matrix that will give you this is the same equation that will give you the circle. Okay? You can go back to the animation and play around and you see it, you're gonna exactly have this, that the distribution here will be almost, they will fill a circle here. And you can make the circle bigger and smaller by choosing the sigma number. Is that clear? So let's see how much time. Okay, good. Now let's look at something completely different. I mean, let's level up. So now you've seen the Kalman filter. And now let's see, we've only solved with the toy problem so far, right? The 1D problem, the 2D problem. What about the real sensors, right? What about fusing the IMU with, the IMU itself was already multiple sensors. Remember, the IMU had 3 magnetometers, 3 accelerometers, and 3 gyroscopes. And you remember when we had the experiment here in the lab and, Tariq was playing around with the IMU, you saw that it was very accurate. It was not being affected, for example, when Tariq, moved his phone or moved something that was metal. It was not affected by that. So the PX4 actually was implementing already a Kalman filter for you. So how do we implement the Kalman filter for something that's in real life? The answer is you cannot use this normal, the standard Kalman filter I showed you for the following reason. It's not enough. Because simply, we had one big assumption that the dynamics and the sensor models, they are linear, right? They were given by the F matrix, the B matrix, and the H matrix, and these were all linear equations. In real life, everything is nonlinear. Okay? In real life, all of the camera, how the camera affects, the dynamics of the robot, how even the accelerometer itself, the accelerometer and the gyroscope and the magnetometer. If you go back to the lecture when we had the sensor modeling, so on topic number 3, you'll find that there was sines and cosines all over the place because of the rotation matrix, which means that everything is nonlinear there. So there are many ways how you can treat nonlinearities with the Kalman filter. One of them, which is the most popular one, is called the extended Kalman filter. The extended Kalman filter as an idea is very simple, and as a performance is actually very powerful. And that's why people love it a lot and they use it really extensively. Okay? Even though it has some limitations of its own, but it's still much more usable, and it's much more powerful than the Kalman filter. And the whole idea simply is that it does something called linearization of the nonlinearities. You're all familiar with linearization, right?
Yes.
Right? In what sense did you take it? What course? Linearization? Algebra. Linear algebra?
Yeah, Taylor series. I think math.
Taylor series, yeah, exactly. Does that ring a bell for everyone? A long time ago, it's ages ago. Okay, so I'll remind you a little bit of what you should already know from that course. Okay, so it all goes back to Taylor series. Okay, so Taylor series again is this expression. It says the following. Okay, if you give me any function that eats n variables, so x1, x2, x3 up to xn, and it gives me one real number in the end, okay, then the Taylor series expansion of order k. Okay, so you can specify I want Taylor series expansion of order 1, order 2, order 3, as much as you want. So of order k, and you do the Taylor series expansion around some predefined vector. So you choose, for example, I want to linearize or I want to approximate the function around some x0. Then you would express fx as the sum of k derivatives evaluated at x0. Okay, so I just use the k derivatives. In the case k equal 1, which is the easiest one to look at, and the one that actually we're going to be using, you can approximate any function f of x to be the value of f at the point x0 that we're talking about, this vector x0, plus the gradient of it, df x as a function of x0 multiplied by x minus x0. And the df of x0 is simply the partial derivatives, the partial derivatives of the function with respect to the x's. So df of x is simply partial f by partial x1, and then after, as a vector, you have partial f by partial x2, partial f by partial x3 up to partial f by partial xn. So this is the gradient of the vector, okay? Sorry, the gradient of the function f. Rings the bell, okay? Partial differentiation, okay? So nothing fancy here. And afterwards, if I have a function that goes from Rn to Rn, okay? So I eat n variables, and I also give as an output n variables, then I can also do the Taylor series expansion, but it's just generalized to something called the Jacobian. Are you familiar with the Jacobian? Yes. So this is the Jacobian matrix. It is simply, in the first row of it is partial f1 by partial x1 up to partial f1 by partial xn. And in the second row, I have partial f2 and so on and so forth. And in the nth row, I have partial fn by partial x1 and so on and so forth. Okay? So you just make up this matrix, okay? And you call this the Jacobian matrix. Okay? This is very easy to calculate by hand. If the function is very easy, sines and cosines, you all know that, you all know the differentiation rules by heart. Or if you just MATLAB can do it for you in one line. Okay? There are very, numerically or analytically, there are very, well-known methods that you can compute it. Okay? So it's no big deal actually to calculate, the Jacobian. Actually, even if it scares you a little bit, go back and try to digest it at home. But it's very easy to compute it, whether by hand or numerically or analytically. Okay? For the functions that we're going to be treating. So just so that you can capture what's going on. So I approximated f of x as simply this vector plus this n by n matrix multiplied by this n vector. So the whole idea is that can we get this n by n matrix? And if you can compute it, how can we use it in the Kalman filter? That's the whole idea. Okay. So this slide is too much, but if you read it at home, you'll find it makes sense. You just need to connect the dots together. Usually, what we have in real life, we don't have a model like this, right? We don't have this linear model. We actually have a nonlinear function like that. So you say that xk is related to xk minus 1 and related to uk and vk, which is the noise, all through nonlinear function. So I have sines and cosines, and I have square root, and and so on, and squares and quadratic functions, and so on and so forth. Okay? So everything is very complicated there. What the Kalman filter would do, what the extended Kalman filter would do, is that it uses this Taylor series expansion to approximate this equation by that equation. So it's only approximately. Okay? And how do we calculate fk and bk and gk? Simply by taking the Jacobian. Okay? So what is fk? It's simply the Jacobian of f with respect to xk minus 1. And what is bk? This is the Jacobian of f with respect to uk. And what is the gk? It is the Jacobian of f with respect to the vk, to the noise. This is something that we're seeing here for the first time. It's because the noise actually can appear non-linearly. Earlier, we just assumed that the noise was just some additive noise. We always assumed it's just something number and we can use it. But here, it usually has some corresponding matrix that you use. And the G will appear, it will change a little bit the equations of the Kalman filter. Okay? So the only thing is that how can we calculate the f, the b, and the g? Simply just take the function f and do all of this Jacobian calculation. So this is how the Jacobian of the f with respect to xk minus 1 will be. This is the fk. This is how the bk will be. You should take partial differentiation with respect to the u's. And this is how the gk will be. You will take partial differentiation with respect to the v's. Okay? So I started by one nonlinear model, and I got out of it 3 matrices: the f, the b, and the g. Okay? And just even though it's written like this, there's a remark here I put for you that the b itself will never be used in the Kalman filter. You can compute it; it's mathematically valid, but it's actually not needed at all. Okay? So in essence, we're actually computing the f and the g. So partial differentiation of f with respect to xk minus 1, and partial differentiation of f with respect to vk. And the u, we don't need it for the Kalman filter. So we don't need the b. So that's the only thing that we added, okay? Give you a nonlinear model, compute the Jacobian with respect to xk minus 1 and the Jacobian with respect to vk. That's the first thing that you do. The second thing that you do is that you go to the measurement model. The measurement model itself is also nonlinear. So I have that the zk is related to xk and wk through a nonlinear function. No longer is just a linear map. And thus, I can approximate it by taking the partial derivative of h with respect to xk, which is the hk here. And I take the partial differentiation of the h with respect to w, and I get the other matrix, which is lk. Okay? And that's it. Okay? Make sense? So the whole idea of what the extended Kalman filter will do is that it will linearize the nonlinear models, the true models, which are the one for the state transition model, which is nonlinear, and the measurement model, which is also another nonlinear function. It will linearize them to get two matrices, f and g, from the state transition model, and it will get the matrices h and l from the measurement model. After you have the f, the g, and the h and the l, now you can use them in the Kalman filter. Okay? How do we do this update in the? How do we do the prediction in the update in the Kalman filter, and the prediction update and the correction update in the Kalman filter? Okay, using these matrices that we're going to be discussing next lecture, inshallah. But for now, I just want you to practice this idea of the linearization. Okay, so I'll put for you some homework examples today, inshallah. Okay, that along with the solutions, that you can just practice a little bit how, given some function, how does the linearization of it look like? Okay, just play around with some math. Okay, this will be simply just math stuff. Okay, but they are very much related to this, to robotics in this sense, because all of these matrices we're going to be using them in the Kalman filter, which will again solve the localization problem. Okay, so next lecture we're going to be looking at the equation of the extended Kalman filter. Okay, after the quiz, inshallah. Okay, and afterwards in the next sorry. Okay, so we see. For those of you who came late, so the quiz will be next Sunday. So next lecture, on Tuesday, we're going to be looking at the details of these equations, okay? And we're going to be seeing the implementation of the extended Kalman filter, okay? And we're going to applying them to some nonlinear problem. And then next Sunday, we're going to have the quiz. And then we're going to have, after the quiz, there will be some extra stuff, okay, that, just to wrap up this topic. We're going to be seeing how the PX4 actually implements the extended Kalman filter to actually do an IMU measurement, state estimation. Okay. So, any questions? Yes, Mohammed.
Regarding the linearization.
Yeah.
Using Taylor series will make the evaluation of the function inaccurate after a certain interval. Isn't that what's against what we are looking for?
It's okay. So let me rephrase it. When I'm using this approximation of the function itself, does this introduce an error in the prediction? And of course, yes, it does. It's now not just that there's an error because of the noise. There's actually an error because of the approximation that I did, approximating the nonlinear part to a linear part. And yes, that's for sure. Yeah, and that's exactly why when we're implementing the extended Kalman filter equations, next lecture, inshallah, you'll see that we're going to have a mix of both. We're going to be using the nonlinear function whenever we can, and whenever we cannot, we're going to be approximating it using the linear stuff. So actually, we're going to be using both.
So you will do a Taylor series loop every time we need it, or like for example, you take a value of x equal to 7.
Yes?
You're going to do the derivative around that 7.
Around that 7, exactly. We always evaluate. That's another very good point. We always evaluate, and you see here, actually it's written here in this slide. We always evaluate the Jacobians at the last prediction that we had. Okay, so we always use the mean from the previous time step, which is the latest update that we know about the state. We always evaluate it around that state. Okay, And the way how you can do it is that you can either numerically, every time, calculate the f by automatic differentiation, compute the Jacobian by automatic differentiation using some libraries online, some libraries that you can implement in your robot. Or you can actually compute the f symbolically, and then you can just always plug in the latest, x hat from what you have. That's exactly what you're going to be doing in the assignment. Okay, so at least in the homework. Okay, you're going to be computing the f symbolically, the Jacobian symbolically, and then you can use all of these matrices in the code. And in the assignment, you will be given some code, and inside of it, the Jacobian will be just implemented. You'll just have to update the Kalman filter equations. There's some question here. Yes, Abdul.
The quiz will be the same material or?
The quiz will cover everything from lecture 13 up till this lecture, okay? Including this idea of taking on a linear model and try to linearize it. Okay? Yes, Mohammed. One assignment, yes, and one quiz, yes. The assignment I'll post it today, inshallah. Okay, today or tomorrow. Okay, and then it will be due next week Thursday. So you'll have because it will be programming also you need to play around with. Okay. And for the quiz, it's up till this lecture. Okay, so next lecture is not included in the quiz. Okay, even though actually studying this stuff as usual, studying this stuff before the next lecture will make you actually will connect the stuff. Will help you a lot. Okay, if you wait, if you forget about this lecture, you don't use it. You will get a good grades in the quiz. I can get it because it's not included, but the understanding will be a little bit deficient. More questions? Let me stop the recording here.